Good morning. We will continue from where we left in the last class. We were essentially did in the last class looking at second order system, which we are very much familiar, that is our spring mass damper system. And you have learned about how can we write equivalent state space equation and output equation. So you see there are a state variable. So the state variable there, we had two variable. One is the response of the system. Another one is the velocity or the rate of change of response of the system. But we were able to look at the second order ordinary differential equation as two single order differential equation. That's what is an advantage of having the state space form. So if you have nth order system, you would be able to represent nth order ordinary differential equation which governs the dynamics of the system into n single order system, and there will be n state variable and associated state equation and output equation. So this is what we have learned in the last class, and then we were able to represent our dynamics of the system through the control design part. In that way, we were able to represent a block diagram that represent our generic state space equation, and also we have looked at how the same equation, the block diagram can be written for the second order system, which we have seen in the last class. This is what essentially in the last class we have seen, and we will continue from that point and try to complete understanding this Routh stability criterion in this class. That's what is the objective of today's period. Let me share my screen for the same. So if you look at this is essentially what we did in the last class, right? So this second order differential equation, ordinary differential equation, we were able to represent into state equation and the corresponding output equation. And we were also able to write the state equation and output equation for multiple input, multiple output, linear time invariant causal system, and where we were able to define what are these A, B, C, D matrices. And these A, B, C, D matrices are quite useful to find out your closed loop transfer function by this formula. So that's what we witnessed. And we were represented the block diagram for a linear continuous time control system, where it is a generic equation where this A, B, C, D matrices also are function of time. If we consider, it's called a time varying system, and your block diagram represents the complete governing equation of your model. Nth order system, and we were also able to apply the same for our mass spring damper system, and this is what we did in the last class. And then we were just started with understanding what is this Routh stability criterion. So if we have to look at its application wherever the control system design is there, the main objective of representing a control system for a linear time invariant system is one that doing stability analysis. Otherwise, it's called the eigenvalue analysis. So we look at this closed loop transfer function, and the denominator, whatever the polynomial that we have, is what is called a characteristic polynomial, and equating that to 0 is what is equivalent to an eigenvalue analysis. So how does this characteristic polynomial can also be looked at when you look at nth order ordinary differential homogeneous equation. That's what today's class I'm going to start looking at, and then getting this equation and so on to get into understanding Routh stability criterion. So essentially, this nth order polynomial can be factorized in terms of linear or quadratic factors. These linear or quadratic factors can be useful for finding out the roots of this nth order polynomial. If the roots of all the roots of this polynomial lie on the left half plane of your complex plane, it's called the S plane, then the system is stable absolutely. In case you do not have even a single root of this n roots on the left half plane and that lie on the right half plane, then the question of stability comes. The system is unstable. Absolute stability is not ensured. So the necessary condition for any system to be stable, the characteristic polynomial roots called closed loop poles should lie on the left half plane is what we are just looked at and uttered in the last class and stopped our lecture. And I'm going to start from this point in today's lecture. And look at that. Before that, we looked at what do you mean by yaw plane stability analysis. So vehicle stability, when you look at the question is, what do you mean by equilibrium? So equilibrium means if the vehicle goes in a straight line, even it is being subjected to a wind gust in the lateral direction, some sudden disturbance, the vehicle should continue its motion straight. So then the system is stable. This external disturbance can cause this is called a disturbance. It is not going to be an external force throughout acting. It is sudden disturbance acting, and that disturbance, this is going to get disturbed from its static equilibrium. Static equilibrium in the sense what this is going in a straight line with a constant speed is what is the static equilibrium according to Newton's first law of motion. So if that get disturbed, that can be disturbed in two ways. It can set into oscillation or it can suddenly go out of arbitrary motion. So get into oscillation is what is stable equilibrium. And that would die out quickly as soon as this is removed or no, along the due course, that would die out. That's what is similar analogously look at a sphere on this groove is disturbed, it can oscillate and settle down. Whereas another equilibrium point can be this position, but the slight disturbance would make this to fall from that potential and it cannot get back to its equilibrium position. That's what is called an unstable state, and that would be pronounced in your vehicle whenever there is an oversteer tendency of the vehicle driven in this way. And suddenly the speed of this is the critical speed and the disturbance cannot be managed by the steering input, rather the vehicle would turn into the disturbance side because of the oversteer tendency, and that will lead to an unstable state called yaw stability lost. So that is what is called yaw plane stability analysis. So this is physically that we have looked at and we have uttered this in our previous lecture, and today we are going to look at that mathematically from your state equation, right? And along with the Routh stability criterion. So that's what we are going to do. And that's what is we were doing in the last class. The nth order system can be represented by this generic differential equation. So on left hand side, you have a differential equation of nth order describing the dynamics of the system. For the input again can be represented by another ordinary differential equation of mth order. So this equation Roman letter 1 can be represented into an algebraic form, and to get your closed loop transfer function simply by taking on both sides Laplace transform with the initial zero conditions, and you would end up with this closed loop transfer function. The denominator polynomial equating to 0, what is called the characteristic equation of the system, and that is essentially representing your eigenvalue analysis in an algebraic form. And that's where we are going to look at our Routh stability criterion, right? So with that note, let me just start today's lecture. This is lecture number 34. And today's date 15/11/2021. So let's write nth order, first order, nth order equation to represent nth order ordinary differential equation. That's A naught t power n q by dt power n plus A1 t power n minus 1 q by dt power n minus 1 plus A2 d power n minus 2 q by dt power n minus 2 plus and so on plus ANQ equals 0. So equating to 0 is what is for eigen. Sorry. Value of. What do you mean by that? It is free vibrational study or free oscillational study, right? Free vibrational. Free vibrational study in second order system, we call specifically, this is an nth order system. So the term free vibration study is not that off, but connect to what is that on the right hand side is 0 is what is called a homogeneous differential equation that represent system dynamics under its initial state. That's what is the meaning of it, right? How can you represent this into n single order equation is like this. We have already seen that. I'm not going to take defining my state variables like in second order system I did. We can do that. There are many ways of doing it. But this system of nth order system can be represented as n single order system like this. So that would be Q1 dot equals A11 Q1 plus A12 Q2 plus and so on plus A1n Qn. So this is first equation. And similarly, I can have Q2 dot. So this is derivative of my state variable, and here Q1, Q2, Q3 up to Qn are my state variables. And A11, A12, A1n is first row of my A matrix. Like that, you will be able to have. So this equation mathematically can be decomposed into n single order differential equation, right? So this can be A21 Q1 plus A22 Q2 plus and so on plus A2n Qn. This is my second equation. So like that I can have up to Qn. That's so here this derivative Qn dot would be equal to An1 Q1 plus An2 Q2 plus and so on plus An Qn. This is A coefficient. So like this is my nth equation. So like that, the n single order equation I can represent, and this is essentially can be again written as Q1 dot, Q2 dot, and so on, Qn dot. That's equal to, we'll have here inside A11, A12, and so on, A1n, A1n, A21, A22, and so on, A2n. This will continue An1, An2, and so on, Ann into Q1, Q2, Q3, and so on up to Qn. So you can represent this way. So what is this matrix? Is A matrix. Here is state matrix. This is your state matrix. So what is the solution of this set of equation? So the solution of this set of equation can be now obtained by representing Q of t as equal to Q e power st. Right. So if that is so, I will have Q dot of t would be equal to Sx e power st. Like that I can have. See, this is obtained by substituting this in nth order equation. So I can have like that Q n dots t is what is s power n x e power st. So put this in 1. So what is 1? Roman letter 1. So Roman letter 1 is your governing equation. So this is Roman letter 1. So substituting that in 1, I would be able to have my characteristic polynomial. So when I put this with 0 initial condition, with 0 initial condition, I would be able to have now this a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 plus and so on plus an, that's equal to 0. So why? Because q e power st cannot be equal to 0, because this into that I will have, by substituting this in my ordinary differential equation, I'll have this common term out. This cannot be equal to 0 to avoid triviality. So this can be made equal to 0. This is what is called a characteristic polynomial. Characteristic equations are not polynomial. Polynomial should have the other side some value. So this is characteristic equation of nth order system. So how many number of roots for this would be there? Finding the roots of this equation is what is a tedious task. It depends upon the parameters of the system. Though we say a0, a1, a2, an. So these are the coefficients of this characteristic equation. And these characteristic equation coefficients depends upon the parameters of the system. So when I say what do you mean by parameters of the system? If it is a second order system of a bicycle model, the parameters are its mass, its mass moment of inertia, and your dimensions of your bicycle model represent your vehicle, and tire cornering stiffnesses and so on. So those are the parameters of the system, and these coefficients depends upon them. So when you have like a characteristic equation for any system and these coefficients are positive, and that refer to an absolute stability of the system. And importantly, none of this coefficient should be 0. So if you have some 0 coefficient, then it is not going to ensure an absolute stability of the system. If any of the coefficient is negative in this case, it is not going to ensure stability of the system. There itself we can conclude that the absolute stability of the system is not ensured. That's what is called Routh stability criterion. So what Routh stability criterion says, when you look at characteristic equation of nth order system, there are n coefficients, a0, a1 up to an. All these coefficients should be positive. If a0, a1 and so on, an, all are positive, then the system is stable. That's called absolute stability. That's called an absolute stability of the system. Right. So in case if we have even if we have, so this is only a necessary condition. This is only the necessary condition. This is only a necessary condition, but not sufficient. Not sufficient. Why? Because though you have all this terms are positive terms, this coefficient positive value depends upon the parameters of the system. If the variation in the parameter happens, then this any time can turn into negative or 0, then the stability, absolute stability is a question mark. So how would you ensure that? So determining all the time this coefficient positive, what are the influencing parameters also to be identified, and from there you would be able to have a condition, and that condition addition to this coefficient positive condition, which is necessary condition, together can ensure the stability of the system. So that is what is to be looked at. So mathematically, one can get this equation, look at the coefficients positive, and you can conclude it's absolutely stable or not. That's one advantage without even finding out the roots of the equation. That's what is the Routh stability criterion advantage. So this criterion says don't require to find out the roots. So what is that general procedure? Having these roots, ensuring them all are lying on the left half plane is what is the stable state of the system. But if it is a second order, first order, second order, smaller order system, you can find out easily the roots of the system and you can say. But if you have really nth order system and you have n roots, finding it's complex, as we have seen that this characteristic equation can be factorized partially into linear and quadratic equation. And then you are making an attempt to find out you have your complex roots. So complex roots to positive real part refer to an unstable state and so on. So that step can be skipped if you are understanding what do you mean by Routh stability criterion. So this criterion says the following steps I am going to explain once you have your characteristic polynomial with these coefficients, right? So let's look at those steps. So you have the first step, you have this characteristic polynomial a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 plus a n minus 1 s power 1 plus an equal to 0. So this is your characteristic equation. So in this an should not be equal to 0. This constant term here should not be equal to 0. That's an essential thing. If that is going to be 0, what does that mean? There can be roots which can be 0 roots, right? Any 0 roots that is be there. So having this condition, the 0 roots are removed. You can say this is step number 1. So when you look at this polynomial, you see that this is not equal to 0, and that's step number 1. So what is step number 2? In step number 2, you have to look at whether these coefficients are all positive. And if it is all positive, you can comment on absolute stability of the system. So step 2 is observation of a0, a1, a2, and so on. And a1 all are greater than 0 to ensure the absolute stability of the system. Absolute stability of the system. But as it is said, it is necessary condition, not sufficient. The dependency of parameters, what you have to do is, you have to go in for the step number 3, where you have to arrange this all coefficient in a particular fashion. Step number 3, arrange these coefficients in this following fashion. So I would have now some arrays now. So I will have first column representing my this orders s power n minus 1, s power n minus 2, s power n minus 3, s power n minus 4, and so on up to s1, s0, right? So if I have nth order system, nth order characteristic polynomial, I will have how many number of rows? N plus 1 number of rows. So in this rows, I should arrange my coefficient of the given nth order system in this fashion. So I have a0, a1, a2 like that. So I should have all even subscript coefficients first on this row. So that is a0, a2, a4, and so on like that. So a6 like that I should arrange. And in my second row, that is s power n minus 1 row, I should put all odd number a1, a3, a5, a7, and so on like this. So once we arrange, now the third row that is corresponding to s power n minus 1 term would be now B1. So B1, B2, and so on. So how do I get B1? So this B1 is obtained by doing this operation. So what I have to do, I have to multiply this A1 with A2 minus A0 A3 by A1. So this B1 would be A1 A2 minus A0 A3 divided by A1. So look at this operation to be carried out. So A1 A2 minus A0 A3 by A1. So I take this A1 A2 minus A0 A3 divided by this is what is B1. So what would be B2? So B2 is A1 A4 and A0 A5 divided by A1. So A1 A4 minus A0 A5 divided by A1 divided by A1. So if I ask you what is B3, you'd be able to write B3 would be A1 A5 A1 A6 minus A0 A7 by A1. So I can continue like that till I get my B1, B2, B3s are coming. So if you look at this process would make into a triangular fashion the terms, right? So now the C1, C2, C3 corresponding to this row. So the C1, how do I get? I'll have to look at now B1. So B1 A3 minus A1 B2 by B1. So C1 would be B1 A3 minus A1 B2 by B1. And similarly, C2 would be what? B1 A5 minus A1 B3 divided by B1. So C2 I'll get. Like that I can continue. So in this way, I should continue doing this. So if I have to go for D1, so D1 would be what? This. So C1 B2, D1 would be C1 B2 minus B1 C3 divided by C1. So like that I can continue and have my D2 and so on like that. So here it is some F1 G1 it is ending. So here I'll have one term finally, and this is how it will be in a triangular fashion. So this is the first task. So step 3, I have to arrange this coefficient, first even coefficients and then odd number coefficient in this, and then find out complete this process. So now I'm not finding the roots of the polynomial. Rather, I'm doing this method proposed by Routh, and that's why it's called Routh stability criterion. So after doing this all, what is that I should do is I should look at the first column of this. So if this first column, if I have all the elements are of same sign, A0 is positive, A1 is positive, B1 is positive, all are positive, that means it is absolute stability. I'm not looking at first thing. What is that you have looked at? You have looked at A0, A1, A2, all are positive. A0 is 0. Then itself we can conclude it is stable system. But that is not sufficient. That's necessary, but that's not sufficient because there can be dependency of parameters. That is to exploit. You should go through this procedure and double ensure it is now. So this is all again positive, like B1, C1, D1, all depending upon these coefficients, right? So these all are of same sign, then in this absolute stability and it is a stable system you can conclude. If you have here positive, positive, suddenly negative, then positive, then negative, then there is a sign change in this. So how many number of sign changes are there? That many number of roots are there on the right half plane. Then the system would be unstable, you would say, right? So that is what is the reason why you should do this procedure to carry out. So if you have understood this procedure, let's look at some simple example and then we will do our stability analysis. So I'm just going to take an example of our bicycle model itself, right? So bicycle model itself. So in bicycle model, you had your A matrix I'm not going to write the equation all that we are very much familiar. So this is 2 by 2 and that has got an elements here A11, A12, A21, A22, right? So what are those elements? Just to recollect, I'll write down those matrix so that it will be now investigated. So I have this C alpha F plus C alpha R by mu. This is my A11 term. A12 term in my bicycle model state matrix was minus A C alpha F plus B C alpha R by mu minus u, and A21 term was minus of A C alpha F minus B C alpha R by I Z u, and minus A squared C alpha F plus B squared C alpha R by I Z u. So this was our state matrix, right? State matrix that we have seen. So what is that you are going to do with the state matrices? This. So if I have this, I know now my characteristic equation. How can I get it? So the characteristic equation to get, I just do this, right? So here my equation Q equals x e raised to st. So if I substitute that in q dot equals aq, right? So in this I have to put, so what is that I do? I also get its differential. So that's going to be s x e power st. So put this in this. If I substitute, I get si into x e raised to st. On the other side, I have this A matrix into Q, that is x e raised to st. So if I bring on this side, it's going to be si minus A into x e raised to st. That's equal to 0. So for non-trivial solution to exist, the determinant si minus a, right? So the determinant si minus a equals 0 for non-trivial solution to exist. So if I have to do that, what is that I'll have simply this. So let's just work out that. So it's going to be this determinant. So yes, I. So I is the identity matrix. Here it is 2 by 2 matrix size I consider. Just to look at my bicycle model terms here. So it's going to be yes. So this is first term here would be s minus a. First term is a11 and minus a12 here, and here it is minus a21, and here it is s minus a22. That's equal to 0. So this determinant would be s square. So if I do cross multiplying, I carry out this s squared minus a11s minus a22s plus a11 a22 minus of minus, so minus a12 a22, that's equal to 0. So I would have now this is s square minus a11 plus a22 into s plus a11 a22 minus a12 a22. That's all equal to 0. So now you have to compare this with our characteristic equation, that's a0 s square plus a1 s plus a2 2. That's equal to 0. So if I have to compare this, I have now here A naught. So what is the condition, Routh stability criterion? If I have this, in this A naught should be greater than 0, A1 should be greater than 0, and A2 also should be greater than 0. So this is what is Routh stability step 1. So you look at this and these are positive, then you say it's absolute stable condition. But now you see A1 is now given by what? This term minus A11, A22. So here I have this minus and this A1 is equal to, so in this what is A1? A1 is equal to minus of A11 plus A22. So if I look at this minus sign, if A11 and A22 are positive, this sum is positive, then it is minus, so I would say this is unstable system. But that's what you have to look at. These terms are going to get influenced by vehicle parameter, right? So this is my A1 and A naught of course is equal to 1. A1 is this. What is my A2? A2 is this. A11, A22 minus A12, A22. So I have to find this. So again, this can go into negative. If this goes into negative, then the system will be unstable. So this imposes the condition always this A11, A22 should be greater than A12, A22. So like this, you would be able to get to the conditions required for stability of the linear time invariant system can be found out. So that's what is an advantage. Without having factors or the roots in hand, you would be able to talk on stability, absolute stability, and find out if it is unstable, what is the influencing parameters from this criterion. So if I apply this criterion into my bicycle model now. So in bicycle model, what is that we have seen? We have our A matrix written here. So we have this A matrix. So look at now. I have here this is minus and here also it's minus. Look at inside this bracket, this is all the positive terms. Here also it's positive term. So when I add these two, it is minus of this. So in this A1 would be minus of this. So the minus goes and that become positive. So if you look at now for my bicycle model, for yaw stability analysis, what is my, this is corresponding to this. So A1, A naught is 1. If I carry out this, S minus this plus and S minus of this. So when I carry out that, A naught is 1 and A1 would be now this minus of these two. So that's going to be C alpha F plus C alpha R by mu plus A squared C alpha F plus B squared C alpha R by I Z U. So this is positive again. This positive term. So A naught is positive, A1 is positive in my bicycle model. What is A2? So A2 now is A11, A22 minus A21 minus A21, A12. So if I do that, I should multiply this. So C alpha F plus C alpha R by mu. So minus into minus become plus, and this is going to be A squared C alpha F plus B squared C alpha R by I Z U minus this. So see here, if I take this, this is not minus common out, so I would have these two terms, right? So if I take this minus of this minus this plus. Plus, and I would have this A C alpha F minus B C alpha R by I Z U into this term, that is A C alpha F minus B C alpha R by mu mine plus u. So this product. So if I do this all, I should see whether I get a positive value or negative value. So that's what is very interesting. If you just work out this, and you would realize if you work out this, you would realize A2 would be equal to this. If you work out, you have terms to be multiplied and common term you take. Finally, you would see that it would be appearing like this. So this A2 would be equal to 1 plus m into BC alpha R minus AC alpha F by L squared C alpha F C alpha R into U square. This is all in terms here. So it will be like this. So this A22 comes out to be like this. So this has to be positive for stable system. So the condition here is this should be greater than 0. So you see there is a minus sign here. So if this term is greater than this term, then it is always positive. But if this term is smaller than this, there will be negative term, and here that can go beyond 1. There is a chance that this term is going to turn into negative. If that is going to be negative, then the system is unstable. So that's where we were representing this as 1 plus K3 U square, and that should be greater than 0, where this K3 is what is stability factor. So like that, the stability factor for nth order system also you will get. Every system you will have many stability factor. Since it is of second order system, the stability factor is what you get it to ensure that this term to be positive. So what is this K3? Is m into this. So this is what is K3. This entire term is what is K3, right? So when K3 is negative, when this K3 happens to be negative, you know that's going to be oversteer tendency of the vehicle, right? When K3 is negative, then there is a chance of unstable state. That's what he said. And what is the condition? You are going to make this equal to 0 and find the speed. That's going to be 1 by 1 minus K3. So this is what is your critical speed. So at this particular speed, you see that your vehicle can no more can be exercised with the steering, and it would go spinning on yaw plane, and that's what is an unstable state of it. So how do you ensure you are able to identify there can be an unstable state? Even the design is of originally oversteer tendency vehicle, so you should be cautioned with this condition that the critical speed of that such vehicle should not be more. So you would be able to ensure the stability by riding your vehicle below this speed. So that is how you are able to look at now. I have not found out the roots of this characteristic polynomial. I can find out that, and then you see that would have the roots lying on the left half plane. But without factorizing, without finding the roots, you are able to talk on the stability with the help of this criterion called Routh stability criterion, is what you have learned today. So we have seen that how can you apply that on a bicycle model, and you are able to define the stability factor, and which already also we have seen that, and today in this particular context it's very clear, right? So now let's look at some example. If I have more than second order system, I'm just going to look at the system mathematically, and I'm going to see, right? So let us just look at this example problem. I have here an example problem. We do not worry about the system physical description and so on. So this is fourth order system. So when I say fourth order system, I will have it's defined by fourth order ordinary differential equation with an input order lesser than or equal to this fourth order system. But we are not worrying about its governing equation, description of its physical system and so on. Rather, we are going to look at now to understand this Routh stability criterion procedure. I'm just looking at the given characteristic equation of this fourth order system. So that is s power 4 plus 2s cube plus 3s squared plus 4s plus 5, that's equal to 0. So this is that fourth order equation, characteristic equation. So now how do I apply my criterion? So first step is what? Looking at the coefficients. So A0 1, A2 1, A3 2, A4 A3 is 4 and so on. So all are positive coefficients. So absolute stability is ensured. That's what you are seeing it, right? But you should have to analyze it. You have to ensure it. You have to ensure it. So it's not sufficient to comment on that. So what am I going to do? I'm just going to take now this array. So it's s power 4, s cube, s squared, s power 1, s naught. So it's fourth order system. I have now 4, 5, n plus 1 terms and the corresponding rows. So I should start. This is what A naught. So here, what is A naught is 1, A1 is 2, A3, A2, sorry, A2 is 3, A3 is 4, A4 is 5. So I should first row odd number. So 1, A3 is 3, and A5, first one is even number, A0, A2, A4 and so on, right? So that's 1. So I should write first this row. That's 1, 3, 5. And the next row I have 2 and 4. 2, 4, and then this is 0. It's not there. So now I have to find B1. So just to circle this. So this term here would be what now? That would be B1, which is 2 into 3 minus 1 into 4 by 2. So how much it is? 6 minus 4 by 2, it's 1. So I will have that 1 here. And then B2. So B2 is what? 2 into 5 minus 1 into 0 by 2. That's going to be 10 by 2, 5. So this is 5. Right? And that's all. There's no term after that. So C1. So C1 would be 1 into 4 minus 2 into 5 by 1. So it's going to be 4 minus 10. So what does happen? Minus 6 by 1. So I have here minus 6. So look at interesting. And then I have to get here, it's going to be 0. And this term to get this. So D1 will be equal to minus 6 into 5 minus 0 by minus 6. So I get plus 3. This is 3. Plus 3 or so 6 into 5. So plus 5. So this is 5. So there it ends. So now you see this column, you have to look at it. So though by observation, Routh stability criterion, I have these all terms are positive. These all are positive. That's a necessary equation for absolute stability. But the system is stable or not to see how many roots are lying on right of plane, if at all it is there. So for that I should look at this now. This column has got now, this is positive, positive, positive. There is a sign change. The negative 2, again there is a sign change. So what does that mean? There are 2 sign changes in this column, and that refer to there are 2 roots has got positive real parts. There are 2 roots have positive real parts. So system is unstable. So the system is unstable. We should control like that. So though here you have this first site, you have this positive condition, that is end, that does not end. You should arrange it, and then you have to see is there a column all are positive of the same sign. There is no sign change, then only you can conclude. If there is a sign change, how many number of times the sign changes? So from here positive to negative, again negative to positive 2 times. So there are 2 roots of this have got the positive real parts that lie, those lie on right half plane, right half as plane, and that is saying that system is unstable, right? So this is how you should proceed doing it. So there can be chances in this column. You have suppose a 0 value comes here when I calculate, then what to do? And then 0 value, I will consider that 0 value replace the smallest positive number, and then I will carry out the procedure. and then again I will comment like that, right? And there can be also a possibility that you can have one row completely zero. In such cases, what to do? So like that, there are different special cases are there, and those are explained in textbook Ogata. I leave it to you to go through that. And this is what is Routh stability criterion. So this Routh stability criterion, if I have to apply it for second order system, and that is for our bicycle model, that's what we have just seen here. Its characteristic equations. Instead of finding the characteristic polynomial, I just have my A matrix. And from the A matrix itself, I just be able to write this and see that condition derived. So this is understood for the bicycle model. For any of the physical system, you would be able to apply this Routh stability criterion. It has been given due importance in linear control system design and a very popular stability criterion. And that's what you have learned, and you have looked at in a bicycle model, and you are able to recognize that the stability factor, what with the beginning we were talking on, is come here to impose the condition that the critical speed depends upon the vehicle parameters, wherein you look at that depends on its mass and the dimension and the cornering stiffnesses and so on. All right. So this is what is you understood. I stop at this point, and we will have one more lecture on rollover stability, and that end the handling dynamics, and thereafter we will look at some 10 lectures also for to cover up longitudinal dynamics, wherein we are going to study about acceleration, braking in straight line, and gradability in straight line, and then we will look at the significance of ABS, anti-lock brake system, and we also look at the transmission system needed for your IC engine based vehicle, all put together as a longitudinal dynamics. And then in tire dynamics, we will look at some important tire models and basic theory, how this the tractive forces, lateral forces, or aligning torque, all are developed at the tire road interaction, and we will end our course. So that is a future lecture plan. So with that, I will stop today's lecture, and I'm happy if you have any doubts, I would answer. Otherwise, I would stop.